Hello and welcome. Now in this video, we'll take a look at how to trace cryptocurrency that was sent to a mixer. Now we want to break down three key stages of mixing process, deposit, mixing itself, and then withdrawal, and then effectively show you how to analyze each one of those stages. So along the way, we'll explore some challenges of manual analysis, role of advanced machine learning models play in such analysis, and then of course we can look at some tools that we can use when we need to and don't have access to those large language models to analyze large sets of data transaction. So let me give you a little context what we're going to look at. We're going to look at an actual hack that transpired in 2021. This was a hack of EasyFi. EasyFi got hacked, a whole bunch of money was stolen, money got laundered through many chain hops and mixers, but one of those was there was a chain hop that occurred between Ethereum blockchain onto the Bitcoin blockchain. Once the hacker got to the Bitcoin blockchain, they broke the money up into multiple wallets and start sending them through the mixer. Now we will look at two particular addresses just to kind of keep the cluster in visually appealing and manageable. We'll look what kind of happened through those mixers and how we can make some sense out of it. And essentially, the hacker withdrew the funds, sent it back to the bridge, and bridged it back to the Ethereum network. All right. Now, the first thing we need to do in order to understand what's happening with the mixing process is understand how the mixer works. Now, this is typically where you want to complete some of your own transactions on the mix using a particular mixer you're interested in. Now, that is if it's not a sanctioned mixer, if it's not illegal, and you got a sign off by your legal department, you've talked to your attorneys, and everything's good. You're going to want to complete as many transactions as you possibly can to develop a what we call a ground truth data set, meaning that you know for a fact that this is the address where the funds were deposited. This is how you withdrew them, and you start to have an idea of what's actually happened in the mixer. Now, in our case, we can't do that. We're going to analyze a chip mixer, one of the most popular mixers up until it was taken down by the U.S. Justice Department in I think March of 2023. So it was not too long ago, but it was quite popular, and it's still very relevant. And it's relevant because the approach that we're going to take in breaking down the this mixing process is the approach you can take to whatever else you may have or might be your use case may be. So since we don't have a set of transaction data that's our ground truth that we completed and we know, we'll do the next best thing. We'll hop over to the Wayback Machine and look at the chip mixer site to understand a little bit how it used to work at a very least. All right. Okay, so here we are. Frequently asked question, the chip mixer site. I highly encourage you to kind of read through this on your own in detail to get a real sense of what's happening. But there's a few points that I want to cover here. So ChipMixer creates Bitcoin addresses and funds them with specific sizes. Those chips, these are chips with 001, 002, 004, and so on. When you deposit your Bitcoin, you receive the same amount of chips. For example, if you deposit 0.112 Bitcoin, you'll receive 0.064 plus 0.032 plus 0.016 chips. Each one of these chips was funded before your deposit. So there's no link between them and your deposit on a chain. This is the very first and one of the most important parts here. So what that means is that, listen, you're going to deposit a amount of Bitcoin into the mixer. The address you use to deposit this in is not the same address as that will be used for you to generate your withdrawal. And the next important thing here is that they are predetermined sizes of chips. And that's for a reason. We call this an anonymity set. This anonymity set of predetermined values is created so it's much harder to track because, as you can imagine, many of these transactions happen in one time, all with the same values. It's obviously much harder to track the transaction. That's why they're called anonymity sets. Now, you should also know that this chip mixer offers your ability to take that single transaction that you deposited, split it into multiple other transactions. Also, you can take smaller transactions and merge them into one. And another important thing is that how withdrawal is going to happen. There's quite a bit of other things we could discuss here, but these are the three most important I want you to get out of it. So once the once your withdrawal is actually funded, you will be given private keys to that wallet so you can actually complete your withdrawal. Now, what that means is that the chip mixer folks, those who are maintaining it, also have a copy of those private keys. Now, that's important for you to know because that will obviously influence the user behavior. Because no matter how much you trust the chip mixer, the fact that somebody else has your private keys or private keys to the wallet that your funds are in, you're going to want to move that as quickly as possible. Now, it doesn't mean that always happens, but it does mean that folks are motivated by getting those funds out as quickly as possible. So you can obviously manipulate the timing of your withdrawal, which makes it even harder for investigators to follow because you can kind of delay the withdrawal up to 7 days. But again, it does happen, not very often because people using the mixers are eager to get their funds out. So that's a little bit about the mixer. Now I'm going to jump back into the graph, and now I'm using Merkle Science for the graphing tool. I'm not affiliated with Merkle Science, just one tool I like to use. We'll also look at Dune, which is an analytical tool that I'm going to be using. Not affiliated with them either, but I really like using it, and you'll quickly see why. But let's, we kind of have an understanding what's going on here. Now let's go back to our graphing tool to see what that looks like on the graph. Okay, so as I told you, so I just picked two random addresses. One deposited 19 Bitcoin into the mixer. The other one deposited just a little bit over 12. Now, what's important to note here is that we're gonna chunk this up into three distinct stages: the deposit, the mixing itself, and then the withdrawal. And it'll make it a little bit easier to understand. Now, what we're trying to do with each stage here is to understand how it works, and more if we can, if some patterns are repeating, so that we can kind of start to relate certain patterns to chip mixer transactions. So the first things first, I'm going to open this cluster up, and I can't really decluster it, manipulate it because it's a predetermined cluster. So I apologize, and it's going to get messy really fast. But there's a couple of things that we can learn really quickly. And so let's take a look at it. So our hacker2 is at the top. That's the green. That's the orange line pointing to the address number 1 MCAE, and the hacker1 is red at the bottom. Hacker2 is at the top. One is red, one is orange. And what you can see in both cases, and let's start with the hacker2 on top. It's a little bit cleaner. 19 Bitcoin was deposited in the address 1 MCAE, and that's where the money stops. Now, you're going to see a lot of other orange lines going over to the withdrawal side of things, but they're coming from different wallets. So that's what we learned when we read the Q&A, right? On the chip mixer side, we know that, hey, the funds will go into one wallet, but the withdrawal is going to be funded by other addresses. So we know this is our stop in the chain, dead stop in the chain. Same thing happens on the bottom side with the hacker1. What we can also learn, if you pay attention, is that all these addresses start with 1, right? These are paid to public key hash addresses. These are the original Bitcoin addresses. But that's good for us because we now know that is the pattern that the chip mixer uses, and that's the address pattern. Now, we also know if we take a look at some of these values that are, let me see if I can zoom in a little bit, and hopefully you can make some sense out of it. Some of these values are repeating very often. You can see here the 0.0015 is repeating. You can see that the 0.458 is repeating. You can see that the 0.1825 is repeating. So those are our anonymity sets. We expected that. So now we can kind of see what that looks like visually. We know that the money is going to go into one address. It's going to stop there. We know that the chips will be flowing into the withdrawal side of things from addresses that are already pre-funded. And we know that these chips will eat in predetermined sizes, so we can start to recognize that. Now, next thing I want to just draw your attention to is let's take a look at hacker2 here. This deposit happened at in the block 679880 on April 20th, 2021. That's when the deposit happened. Now, the withdrawal did not happen until block number 679885, April 20th, so the same day, but it's 5 blocks later, right? And this is going to be very important when you start to conceptualize the large amount of transactions you have to analyze to start demixing this thing, and that's why obviously, um, the enterprise companies that serve the enterprise market, they use the large LLM models, and they're usually proprietary because it takes quite a bit of time and money to set them up and tweak them along the way because these things keep constantly changing. Now, show you a different example here. Hacker one, that those funds were deposited in block 680020, and they are withdrawn a little bit sooner, 680022. So you're going to have to look at quite a few blocks to start matching up these transactions. Now, keep in mind that I only picked two, and there's 30 plus transactions within this particular hack, if not more, that you would need to go through. So it's quite a bit time consuming, specifically if you're doing it what I would call manually, like we're going to demonstrate here today. All right, so what do we know? We know that the chip mixer uses addresses starting with 1. We know that the funding of the withdrawal is done from pre-funded wallets in predetermined transactions. And we now know that the withdrawal is set effectively when our appeal chain stops. So we'll look at this hacker 2 again. Let me open all this up. And again, I apologize. There's really no way to keep it too clean. But again, you'll note that once the hacker withdraws here, that's the end of appeal chain. All the funds are withdrawn and then sent over. Now, in this particular case, they were sent over back to the bridge to be sent over to the Ethereum network. They came from Ethereum network to Bitcoin, got mixed, got convoluted, and they were sent back after the mixing service. Now, so that's what we know so far. So that happened on the bottom, that happened on the top, and now the question is, okay, well, we know we have on the top side, at least in Hacker 2, there's about 5 blocks worth of transactions that we have to analyze. Now we know this because I've already done it, but if we didn't, right, we still have to just know that we're gonna have to pick a certain size of blocks that we're gonna have to analyze. So imagine we're gonna go block by block, or there's a couple of different ways, but we'll get to that just shortly, right? And we know that the bottom one was basically essentially 1 block later, right? So what can we do? How can we analyze this large sets of data and make sense out of it in a most efficient way? Now, there's a couple of ways, but one way is we can use APIs to pull the transaction data by block, like crypto APIs is one I use quite a bit if I'm in a terminal. But if I'm not in a terminal and I'm working with large sets of data, I also enjoy Dune analytics, and I'll switch over to that, and I'll kind of tell you a little bit about it, and then we're going to look at an example. All right. Okay, now here we are. I'm just kind of sharing with you the pricing model. Now, Dune is a community-driven platform, and they provide tools to query and visualize and share effectively data from across 75 blockchains. And I wanted to share this slide with you, just because you can see that their free tier is actually generous tier, and you can get quite a bit of work done. And for what they offer, the 75 blockchains and the amount of data that you can play around with and use in your investigation, even the paid version is reasonable. Again, I'm not going to say cheap or anything like that. That's for you to decide. But again, it's reasonable based on the amount of access that they allow you to have. So I'm going to basically share this platform with you in the video description, along with a bunch of other tools. But I'm going to jump over to a transactions analyzer that I set up, and we'll take a look at how it's set up and kind of what we got out of this process. Okay, so here we are in my account here. I just created a blockchain forensics folder, and I'll share this link with you so you can play around with it, fork this transaction, make it better, do whatever you need to. But essentially what I'm doing here, this is using SQL. I am selecting to query data from Bitcoin blockchain. And what I want to display the data in Bitcoin, and I also US dollars. Here are the columns that I want to see. So the block date, time, input counts, values in both Bitcoin and USD, of course, fees, the amount of outputs, and all of that. And but this is probably the most interesting part. So, and Now, based on my analysis of the mixture and what we learned in the beginning, I'm going to filter these transactions. Now, remember, okay, this is the Hacker 2 one. So this block that we're analyzing is 5 blocks later from when the deposit happened. And this block happened to have about 1,500 transactions. Now, that's a low count of transactions for Bitcoin today. Bitcoin processes about 6 blocks an hour, and an average block, I believe, right now is about 5,000 transactions. In any case, you're always going to be between 5, 6,000, maybe even. So that's quite a bit of a large data set. But even 1,500 transactions in our case is quite a bit. So based on what we learned, and this is why I said it's important to understand how that mixer works. Now I'm going to filter for a few things. I'm going to go block by block because I don't want to get 5 blocks worth of data transactions. I want to go block by block. And so I'm going to first filter by block. As you can see, block height here. I'm going to look for specific output values, input-output values. And because I know that they're all of the input addresses will start with 1, I'm going to look for those addresses that start with 1. And because that's the end of the PO chain as well, doesn't always have to be. But again, for this example, I'm going to look for output to the end of that PO chain with a single output, right? So right there, we go from, with just these few simple, by the way, with just these few simple queries, or filters, I should say, I apologize. We're going to narrow down our transactions from 1,500 that was available in that block to 10. And in this particular case, this was the easy one. We can see that there's our value right here. There was 5 inputs, 1 output. It's very close to the same value of 19 that we're looking for minus the fees as was going through it. And you can look at the rest of the data. Now, if I change it to I'm going to actually change it so you can see for the second example that we have, and I'm just going to pause the video briefly, just while the computation finishes, so you're not just kind of sitting there waiting for that to finish. All right, well, I changed the block sizes and the values that I'm looking for, and right away you can see again that was a block size was roughly, again, about 1,600 transactions as well. We got this down to 18 rows, and you're going to see that you can fairly quickly spot the 2 values that add up to what we're looking for. Remember, that was just a little over 12 Bitcoin. So I have the first transaction that's 10.24, and if we scroll down here somewhere, there's the 2.08 transactions. They both have multiple inputs, single output. And if we look this out, what's happening inside this transaction, we quickly realize that yep, that's what we're looking for, and that is our target withdrawal address. So again, I just wanted to show you 2 examples. Keep in mind that there are many more. It's not always this direct, and you'll have to dig in and play around with your filters and what you need to do. But to get you started, like I said, I'll have this particular query linked into the video description, and you can fork it and kind of take it from there. So I'll jump back into the graph, and we're going to wrap this video up, and hopefully you're getting something out of it along the way. All right, so what did we learn here today? So we learned the importance of understanding, reading whatever documentation is available, even if it's just a frequently asked question, from the mixer to understand how the transactions work and look for some repetitive patterns that we can use to identify this mixer. Now, in our case, we were not able to run our transactions ourselves, but we got some description by reading what was available on the chip mixer website, the old website. And we were able to identify that deposit addresses, or all addresses that Mixer uses for deposit and mixing, are the old addresses starting with 1. We know that the mixing is done with the predetermined anonymity set or pre-funded wallets. And we know that the PO chain usually ends with the withdrawal because the user pulls all the funds out. So that we were able to kind of use that to recognize some of those transactions, and then most importantly, be able to apply some common sense filters using Dune to analyze these transactions. Because otherwise, you can imagine, if you were just trying to match up values and the timing, that would be really hard. Now, and this leads me to one last piece, is just to talk a little bit about the block coverage whenever you are doing this type of analysis. Now, if you're setting up a large language model and you're starting with the ground truth set that you've done yourself, and you kind of tweaking the model to understand to set up the right block coverage. In my experience, that can run anywhere between, obviously one and 10. The sweet spot for me has always been about 7, 8. It doesn't have to be. And what I mean by block coverage is how many blocks is your machine learning model, in this case, you going to analyze to achieve the highest number of accuracy. Now, keep in mind, if you pick too large of a block coverage set, if you go, let's say 15, you may end up with a lot of false positive. If you end up, tighten that thing up too much to 3 or 5, even, you might end up, your accuracy will go down drastically. So depending on what type of model you are building and algorithm you're using, you're going to have to kind of play around with the block coverage, amongst other things. But again, it gives you an idea that when you're analyzing these type of transactions, you first want to understand how it works so that you can narrow down your filters, and then what tools might be available to you to analyze large data set transactions. So once again, I will link all of this in the video description. So the Merkle science, the Dune, some research that you can use to review and see how you can set something like this up. I'll also link to a GitHub repository that that you can fork and make your own demixer. Now it's already largely done for particular mixers. So you might have to tweak the parameters a little bit to use it for your use case, but you won't have to start from scratch. So hopefully that'll be quite a bit helpful. And yeah, I think that's it. Thank you for watching, and I will see you in the next one.